All right, this is an example of a projectile that's being shot at a moving target, and that's just going to make it a little more complicated, but we'll work our way through here. So we have a tank 200 meters away that's traveling towards you at 15 meters per second. Determine the initial velocity for a projectile fired at 30 degrees above the horizontal that will hit the tank. So we have some sort of tank coming towards us. I guess we have some sort of artillery thing. It's 30 degrees above the horizontal. We're going to shoot it, and we're going to try and shoot somewhere ahead of the tank because the tank's going to move while the thing's in the air. And then hopefully, if I get my timing right, it'll land somewhere pretty close to right where the tank is when it lands. So first of all, we're going to divide our information up into horizontal and vertical. The initial velocity, we don't know v. We do know it's 30 degrees above the horizontal. So we can find v in terms of the horizontal and vertical separately. V sine 30, which is 0.5 v, then would be the vertical component of that velocity. And v cos 30, which is 0.866. V would be the horizontal component of that velocity. Assuming that this is a projectile and so the acceleration in the horizontal direction is 0, acceleration in the vertical direction is negative 9.8 meters per second squared. Excuse me. The initial velocity in the horizontal direction is 0.866 v, and in the vertical direction is 0.5 v. The displacement in the y direction, even though this tank has some sort of height, it's relatively small in comparison to the height of the overall projectile. So we're going to say the displacement is pretty close to 0. And what we're going to do as we do in all projectile questions is recognize that the time of flight is the same regardless of whether we're talking about the horizontal or vertical direction. And finally, in the horizontal, we want a range that is equal to 200 minus the displacement of the tank. Now the tank says it's moving at 15 meters per second. And we don't know how long it's going to get to move for. Distance equals velocity times time for that uniform motion. So we're just going to call the displacement of the tank 15t. And as long as that t is the same as these two t's, that will represent how far the tank can move in that time while the projectile is in the air. So this will be how far it is away, less how far it is that it moved towards us during the time of interest. Starting in the vertical direction then, I can come up with an equation. D equals v1t plus 1/2 at squared. Substituting my values, 0 equals 0.5 vt plus 1/2 negative 9.8 t squared. So 0 equals 0.5 vt minus 4.9 t squared. Recognizing that usually you shouldn't divide by a variable, but since we are going to say that t cannot equal 0, we're not interested in that solution, then I can divide everything in this equation by a time, and since time isn't 0, I don't have to worry about having done that operation. So this equation is just going to turn into 0.5 v minus 4.9 t, which is a pretty simple equation to work with. Let's leave that alone right there, and then we will, once we get our other equation, hopefully we'll be able to solve that. So in the horizontal direction, d is going to be equal to vt. There's no acceleration, so I can use the uniform motion equation. I don't have to add the 1/2 at squared. So d, or the horizontal range, is 200 meters less the movement of the tank. And that's going to be equal to 0.866 v times t. So this is the motion of the actual projectile in the horizontal direction, and this is how far we want it to go so that it arrives at the tank. A little simplification here. So I'm going to get 200, maybe, 200 minus 15t equals 0.866 vt. Now I can sort of solve this anyway, but I think if I solve this equation for v and then I substitute it over here, it's going to work out pretty straightforward. 0.5 v is going to be equal to negative 4.9 t. Dividing both sides by 0.5. My v is going to be equal to negative 9.8. Actually, sorry, not negative. When I move one of these over, then they get rid of that negative. 9.8 t. With that in hand, I'm going to come up over here to this equation. 200 minus 15t equals 0.866. Substituting my expression for v, negative 9.8. Oh, it wasn't negative. I got rid of that negative. 9.8t times t. Just multiplying out my 0.866 and my 9.8, I get 8.49t. And then I have one more t, so that all turns into t squared. I'm going to bring the 15 over, plus 15t minus 200. And I have a quadratic. I'm just going to use the quadratic function on my calculator to solve this. I'll just use the quadratic equation. I'm not seeing it somehow. T equals negative b plus or minus the square root of 15 squared minus 4 a c divided by 2a. Now I want the positive root here, so I'm going to just use the plus here. That's all that I need. 4 times 8.49 times 200, working inside the brackets first, plus 15 squared, square root of that answer, at 83.8. So I'm just using the plus because I want my overall result to be positive. And I get a hang time of 4.05 seconds. Now with that, I can use this simple equation, 9.8t, to come up with what the initial velocity must have been. 9.8 times 4.05. So I must have launched this projectile initially at a speed of 39.7 meters per second to allow it to come back down and hit the tank at the right time. You could, if you were given a question like this, it's suitably challenging, that you could then start the problem the other way around and say, if I shot a projectile at 39.7 meters per second, would it land at the right spot? The right spot here would be 200 meters minus 15 times the 4-second hang time, which works out to be 140 meters. So the question is, if I had that projectile at 39.7 meters and 30 degrees, would it have a horizontal range of 140 meters? I'm going to leave that for you to verify if you feel like doing it. It will work out though, because I've done it. So that's that.